Have you ever looked at a chart, seen those little eye-shaped error bars, and just kind of nodded along, not really sure what they mean? Or maybe you've read a study and seen two numbers that looked almost identical, but were used in completely different ways? Well, today we're going to clear all that up. We're breaking down two key statistical concepts that trip people up all the time, but tell completely different stories: variance and standard error.
Let's start with a really simple number to see why this all matters so much. Imagine you track your commute for a week, and the average time is 33 minutes. Okay, so what? Is that good? Is that bad? Does it actually help you plan your morning? I mean, does it tell you if your commute is super consistent, or if you need to build in a huge buffer for those days with wild traffic? An average, all by itself, just doesn't give you the full picture, not even close. So to get that full picture, we have to go beyond the average. We need to understand two other really important ideas. First, the spread of all our individual data points. And second, the precision of that average we calculated. And for these two totally different jobs, we have two totally different tools in our toolbox. Here's the best way to think about them. On one side, you've got variance. Variance is like a detective showing up to a crime scene. Its job is to investigate how spread out all the individual clues, our data points, really are. But on the other side, you've got standard error. This is more like an auditor. It's not looking at the individual clues, it's checking the final report, the average, to see how reliable and precise that summary number actually is.
Okay, let's bring in our detective first. We're going to unpack variance and its much more famous cousin, standard deviation. Their one and only job is to look at your raw data and figure out how consistent or how wildly all over the place your measurements are.
So what is it, really? Well, in plain English, variance is just a number that tells you how much your individual data points like to scatter around the average. A big variance means your data is a total mess, it's all over the place. A small variance means everything is packed together, nice and tight and consistent. It's the official number for variability.
All right, let's get back to our commute. Here are the 5 days of data. You can see just by glancing at it, we've got a bit of a range here, right? From a pretty quick 28-minute trip to a sluggish 40-minute one. Our mission now is to put a single hard number on that spread.
Now, don't let the process intimidate you. It's actually pretty straightforward. First, we find our average. We already know that's 33 minutes. Then, for each day, we just see how far off it is from 33. Now, step 3 is the clever part. We square those differences. Why do we do that? It's just a neat little math trick to make all the numbers positive so they don't cancel each other out. After we average those squared numbers, we get the variance. The only problem is its units are minutes squared, which is, well, it's weird. It doesn't make any sense. So for the final, crucial step, we take the square root, and that gets us to the standard deviation, a much more intuitive number that's back in units we understand, minutes.
And after we run the numbers for our commute data, what do we get? We get a standard deviation of 4.69 minutes.
So what does this actually mean for your morning? It means a typical commute for you isn't just 33 minutes. It's more like 33 minutes, give or take about 5 minutes. So on any random day, you can probably expect your travel time to land somewhere between, say, 28 and 38 minutes. This number describes the real-world wobble of your individual trips.
Okay, so we've described the spread of the data. We know our daily commute can be a little unpredictable. But what about the average itself? How much can we really trust that 33-minute number? And that, my friends, is a completely different question. It's where our second tool comes into play.
This brings us to a whole new challenge. Come on, we only have 5 days of data. 5! If we were to do this whole experiment again next week, would we get an average of 33 minutes again? Or would it be 31? Maybe 36? How much can we really trust that one number as an estimate of our true long-term actual average commute?
This is exactly where the standard error steps in. You should think of it just like the margin of error you hear about in political polls. It doesn't care about the spread of individual opinions. It tells you how confident you can be in the overall result. A small standard error means your sample average is probably very, very close to the true average. It is a measure of precision.
And the formula to calculate it is just beautiful in its simplicity. You just take the standard deviation we already figured out, and you divide it by the square root of your sample size, which we call n. And that n in the denominator, that is everything. It tells you the single most powerful way to get a more precise estimate: collect more data. The bigger your sample size n gets, the smaller and smaller your standard error becomes.
So for our commute data with that standard deviation of 4.69 and our tiny little sample size of 5, what does that give us? It gives us a standard error of 2.10 minutes.
So what on earth does this number tell us? It tells us that if we kept measuring our commute in these 5-day chunks over and over, the average we calculate each week would probably bounce around by about 2 minutes. It has nothing to do with any single trip on a Monday or a Tuesday. It's a measure of the stability, the reliability of the average itself.
Okay, we've met our detective and our auditor. We've got standard deviation for describing spread and standard error for describing precision. So let's create a quick field guide. When you're out there in the wild looking at data, how do you know which tool to reach for?
This table really boils it all down. It's all about the question you're asking. If your goal is to describe the messiness in the raw data, like how much does my commute actually vary from day to day, you use standard deviation. But if your goal is to talk about how much you can trust a result, like how confident am I in this 33-minute average, you use standard error. One describes the data, the other describes the statistic you calculated from the data.
Now, before you run off, there are a few huge traps to watch out for. First, with really small samples, like our 5-day commute log, your estimates for both spread and precision can be pretty shaky. It's like trying to guess the plot of a whole movie from a single frame. Second, outliers. One crazy 2-hour commute because of a snowstorm would totally inflate the variance and make your data look way more spread out than it normally is. And finally, please never ever forget this. Standard error is only about the precision of the average. It is the #1 mistake people make, seeing a small SE and thinking the data itself must be consistent. It's not true. It tells you nothing about the range of your individual data points. So the next time you see a statistic with a little plus or minus sign next to it, stop, take a second, and ask yourself, is this number telling me about the spread of the data itself, or is it telling me about the precision of the final result? Because knowing the difference is the key to understanding the real story that the numbers are trying to tell you.